Hi, my name is Sean Thrasher and I'm starting a playlist on multivariable calculus. The videos in this playlist are complementary to my blog and I've put the link in the description. Now to start off, I want to go over a way of conceptualizing functions, a less traditional way. So we all agree that functions are defined as mapping a set of numbers to another set of numbers, right? It maps some numbers from the domain to its range. And I've highlighted a number line here and I call this the input space. This represents all the possible choices of x's I can input to my function f of x. And if I pick an arbitrary point x0, that gets mapped to another number line you can imagine. And if you imagine if I picked another point x1, it might go to another point right here, f of x1 or f of x1 here. It depends on the function. Note that I haven't actually put numbers on these, and that just helps keep the description general. Often what we like to do is to merge the input and the output spaces onto the same plane. And then we define the graph of the function to be all the points such that whatever x-coordinate you pick that lies on the graph, so let's say right here, let's call this x sub 1, right? Then the y-coordinate of that has to be f of x sub 1. It has to be the function evaluated at that x value. Now what happens when our function is defined on two separate variables? Well, x and y now here are thought of as independent variables. So before with f of x it was good enough for you to just give me an x and I can give you a number, right? You give me 2 for x and I say, well, the function is then 4. But here that's not good enough. You have to give me an x and a y. You have to give me two separate pieces of information, two separate numbers for me to give you the actual value of the function. So the way to visualize this is you think of the input space now not being just a number line but being a plane. And these are full of all the x, y pairs that you can pick and put into your function. So if we choose an arbitrary point x0, y0, then that gets mapped to just a number which lies on the number line in the output space, f of x0, y0. Now what happens when we try to visualize this, when we try to combine the input and the output spaces together? Well, again, I can pick a point on the plane in my input space, x0, y0. Now, I define a third axis called the z-axis, which is perpendicular to x and y. Now, if I choose an x0, y0, what this effectively does is that it assigns a height. It pushes it up or down on the z-axis or leaves it there. This is very analogous to how in a two-dimensional function, if I pick an arbitrary x0 here, it assigns a height here, and this ends up being x0, f of x0. This is the same thing going on here, but I'm free to choose any x that I like and any y that I like. So effectively what happens is that this plane gets mapped to another plane, which is called its graph. So before, you can imagine that the number line, the x-axis, gets mapped to a one-dimensional curve, right? In this case, we have a two-dimensional curve, and that's effectively a surface. That's the graph. If we're working in two-dimensional space, if we're working with x and y, right? Instead of y being described as a function of x, which is normally the case when we graph a function, with parametric equations, you define x and y, both separate functions of a third variable, which is often t, which is often called t. So, to be general, if I have my xy plane right here, my parametric curve will be finite, right? And I'll review why it is so in a second. But if I pick an arbitrary point x here, that x is going to be a function of t naught. of t, and then the y is going to be a function of t as well. And I've just put t naught to say that it's a particular point that we're choosing. So x and t are separately defined as functions on t, and the curve is often defined for a restricted domain of t, which ranges from a to b. So one of the most powerful things of a parametric curve is that it can go back on itself like this. A normal function, a regular function, can't do that. For every point on the xy plane, you can represent that with a unique vector such that its tail is rooted at the origin and its tip touches that point. And then if you define the vector like that, then it's going to have components x0 and y0 for a given point x0, y0 on the xy plane. And then you can write that out as x0 times I hat plus y0 times j hat. Now we're going to combine the two concepts here. Now remember that I said any point that lies on this parametric curve is given by x of t and y of t. And if I pick an arbitrary value of t, t0, then I get a point on this curve. And now note that I can define that, I can represent that point with a position vector. Now note that if I picked another value of t, right? I know if I picked here, right, let's say, then we have x of t sub 1, y of t sub 1, that would give me another unique position vector. And the position vector changes as I change the t. And if you imagine, if I increase it, it traces out the curve like that. So it's exactly as if, in fact, it is the case that you give the position vector value of t and then it gives you an actual vector out that tells you the point. And that's very, very, very reminiscent of a function. And that's what it is, but it's not a regular scalar valued function because as you see here, the output isn't a scalar, it's a vector. So r is actually defined as a function of t. And r of t gives you x of t and y of t, to be general. I hope you can see that here. And then of course t is restricted between a and b.